Hello, welcome to another edition of the CNA's Opus. My name's Rich, certified nursing assistant. What we got going on here? This is my lab stuff in here. I don't even know what half the stuff is, to be quite honest with you. There's some stuff here. I don't even fucking know. Alright. Anyway, this is what I'm working on. This right here is HIF1 alpha and HIF1 beta. So that's hypoxia inducible factor 1 alpha and hypoxia inducible factor 1 beta. And in a hypoxic environment in the cell, what they'll do is hypoxia inducible factor 1 alpha will get it will no longer be ubiquinized. So it won't get broken down in the proteasome, and it'll build up within the cell, and it'll dimerize with, see, there's a dimerization here of HIF1 HIF1 beta, or hypoxia inducible factor 1 beta. And once it dimerizes, it goes to a specific region within the DNA called the gene coding region, and that's that's upstream of the promoter region. So this is your promoter region right here, and then this is the gene coding region. And the gene coding region takes specific transcription factors. So this is specific ones. The ones that's on the promoter region are general transcription factors. And a lot of times a common one that you'll a common sequence that you'll hear in the promoter region is something like the TATA box, which is thymine, adenine, adenine, thymine, adenine, and those the organic bases that they bind to in the coding regions is usually between 4 and 10 base pairs long. So that's not out of line with a thymine, adenine, thymine, adenine. So that's just one of them that you'd find in the promoter region. There's not that many of them. There's a lot. I think there's about 31 general transcription factors, and there's a lot of specific transcription factors. And the specific ones, they have about 100 different gene coding regions that they can go to, and they'll act differently. The same transcription factor will act differently at different gene coding regions. So in this gene coding region, it's going to act as an activator or a promoter, an activator. In other regions, the very same transcription factor can act as a repressor, so it can kind of inhibit. And there's different ways that it can do it. But in this video, I'm just going to show one way that it can do it. And hypoxia-inducible factor 1 alpha and beta dimerization in the gene coding region right here will bind to a specific region, and that region is, well, kind of makes sense, hypoxia-inducible factor 1 alpha response element, or the HRE region, and that will that is for the gene for vascular endothelial growth factor A, and that specific allele has 8 different splice variants, and the splice variants are down here. So these little lines that are here, those would be your exons. Those would be your exons, and these in between here will be your introns. So the introns get cut out here, and then the exons get spliced together. But the ones that have variability are the 6th and the 7th. So they have a different amount that can be spliced out, either more or less, at the 6th and 7th region, making 8 different splice variants off of one allele. So this together, this should just be one. This should just be one. This is how it should be each and every time. But that's the primary messenger RNA. Once it gets spliced and put back together, that's your mature mRNA. So in the mature mRNA, you're going to have 8 different mature mRNAs there. okay, when it's just from one allele, not 8 different ones. It's just from one, and that different splicing is going to happen at the 6th and 7th region, and they only form homodimers, which means if you have vascular endothelial growth factor A 121, and I put that's the amount of amino acids right here in the subscript. That's the amount of amino acids that are in the sequence 121. That will only dimerize with vascular endothelial growth factor A 121, not vascular endothelial growth factor A 110. They can't form heterodimers. So that keeps it a lot more simple. It will only form homodimers there. And up here, this looks like a very simple picture that I drew right here. This actually forms a dimerization into a complex called a basic helix loop helix, which I didn't draw out, which would kind of look more like an X right here, and then a loop, and then an alpha helix, and then it has a different structure. I just kept it simple like there, but if you want to look it up, that's the structure that it actually forms, is a basic helix loop helix. So moving on from that, on the HIF1 alpha, by the way, HIF1 alpha and HIF1 beta, they dimerize together at a region called PAS domains, PAS domains, and those are their dimers. That's how they hold together. They hold at the DNA on the major grooves at the hypoxia-inducible factor response element, but they hold together at domains on each one of the proteins called PAS domains, PAS. So anyway, that's the only important region for the hypoxia-inducible factor 1 beta, which doesn't get ubiquinized. Only the HIF1 alpha goes up in a hypoxic environment within the cell. On top of that, it has this 2 prolines here, and it has an asparagine, and the single amino acid letter code for asparagine is N. So we have this asparagine right here, and on top of asparagine, there's a Krebs binding protein that will bind to it, which is a HAT protein. It's a histone acetyltransferase enzyme. So it's going to transfer acetyl groups onto the histone. So if you could look down at this picture right here, you'll see asparagine, but if you could look down at this picture right here, suppose these little square boxes in the middle here are histones, and then the DNA is, it's a helix, it's looping around, but it loops around the histone twice, and then it loops again around the histone twice. That's how we're able to fit about 7 feet of linear DNA into a tiny nucleus. So that's how we're able to do it, is to loop, and loop, and then these histones will actually come together, will coil together. But in order to loosen it, in order to get what's known as the RNA polymerase complex 2, this right here, to the promoter region, which has these general transcription factors here, that these loops around the histone here have to loosen. If it's too tight, this will never get there. So there'll be no, even if it does get there, this will be too tight for it to weave apart and create the messenger RNA. So it's got to be loosened, and then it's got to be spliced. So there's a lot of different things that have to happen. And if this is too tight right here, nothing's going to happen. It just shuts it down. So acetyl groups have to be put on it, and that'll loosen the DNA coils around the histone here. And once it's loosened, RNA polymerase complex 2 can assemble itself because it's a complex of proteins. It can assemble, bind to the general transcription factors. Everything that needs to be done has enough room and area to get done, and then this will go down and start transcribing, and then the ribosome will translate the vascular endothelial growth factor A, and whatever splice variant it is. But down here, under there is the what is this? Oh, this is under normoxic conditions. Okay, so when the oxygen goes back up in the cell and you no longer need the hypoxia-inducible factor, you want to stop creating vascular endothelial growth factor A because you want to stop angiogenesis. You want to stop the production of fibroblast growth factor 2 as well, which is not another thing that's important in did I say fibroblast? Whatever. FGF2. So anyway, that's another important component to angiogenesis, and you want those things to stop under normoxic conditions. And the way that the hypoxia-inducible factor 1 alpha is going to stop, not the way that it's going to be ubiquinized, but just to halt the process of transcribing vascular endothelial growth factor A, is by, there's an enzyme called asparaginal hydroxylase, and that's under normoxic conditions. What it'll do is, obviously it's a normoxic, so there's enough oxygen present, so it'll take off this hydrogen right here. That's off the first carbon, which is and the first carbon is a methylene group right here, and off the methylene group it'll take the hydrogen off right there, and it'll add an alcohol group off the first carbon, off the alpha carbon right here. So there's your alpha carbon, there's your first carbon, and it takes that hydrogen off, and it adds this alcohol group on right here, which then goes down to asparagine, goes down to it's a little bit different than it's not a, I forgot what I was going to say, but anyway, there's an amino group right down here and a carbonyl group right there, but I forgot what I was going to say before that. Anyway, it adds that alcohol group right there. So when it adds alcohol group right there, the Krebs binding protein can no longer bind to it. There's no longer a reaction, so it no longer binds to it or repels away from it, and the DNA will wrap again back tightly around the histones, and transcription and translation can no longer take place. So that'll stop vascular endothelial growth factor, and that'll stop the angiogenesis from occurring, because vascular endothelial growth factor A is one of the important ones. Even though this is in the family, this is the important one. That and FGF2 are two of the important ones in angiogenesis. So I hope that was helpful for your studies, and that'll be it for right now. Rich, CNA, see you later.